Every time you open a website, your request starts with a tiny label, an IP address. It tells the network where to send data and where replies should return. Think of it like a postal address for a device. DNS translates a name, like cyberclarity.com, into numbers routers can actually read. An IP address is not a person, and usually not even a permanent device identity. It is a location label on a network path, and that label can change. Start with IPv4, the version most people recognize. 4 decimal numbers separated by dots, such as 192.0.2.42. Those 4 numbers are 4 8-bit chunks, called octets. Each can run from 0 to 255, giving IPv4 a total of 32 binary bits. "32 bits sounds large until billions of phones, servers, cameras, and routers all need addresses. The total is about 4.29 billion, finite and already heavily allocated. Inside a home, devices usually use private ranges, such as 192.168.1.20. That address works locally. It is not globally unique. Your router uses NAT, network address translation, to let many private devices share one public IPv4 address. Outgoing traffic gets a temporary translation, like a receptionist forwarding calls. That trick stretches IPv4, but it adds layers. Some connections become harder to initiate, troubleshooting gets murkier, and the internet loses its simple end-to-end shape. Meanwhile, the address pool was running out. Regional registries exhausted their available IPv4 blocks, so new networks increasingly rely on transfers, conservation, and translation.
Could we just make every IPv4 number longer? Not without breaking the format and the equipment built around it. The internet needed a new addressing system. That system is IPv6. It keeps the same basic job, deliver packets to a destination, but expands the address field from 32 bits to 128. Now watch the canvas change. IPv4 is a crowded city of 4 billion doors. IPv6 is a continent-sized address map. 128 bits create 2 to the 128 possible addresses, roughly 3.4 times 10 to the 38. The point is not to count them. It is to stop rationing. IPv6 writes those bits in 8 groups of hexadecimal digits, separated by colons. Here is a documentation example. 2001, DB8, 0, 0, 0, 0, 0, 42.
Hexadecimal packs 4 binary bits into 1 character, so the notation stays compact. Leading zeros inside a group can be dropped. 0042 becomes 42. A run of all 0 groups can be compressed once with a double colon. So the long address becomes 2001, DB8, double colon, 42. Shorter, but still the same address. IPv6 also makes address roles easier to see. Double colon 1 is loopback. Addresses beginning FE80 are link local. Global unicast addresses are designed for broader routing. Many IPv6 devices can configure themselves with router announcements, rather than waiting for a central address server. That is convenient, but networks still need careful policy and security. For a long transition, networks run both versions, dual stack. An app may try IPv6 first, then use IPv4 if the path or service is unavailable. Other systems translate or tunnel between them. NAT64 can connect IPv6 clients to IPv4 servers. Tunnels carry one protocol through a network built for the other. Here is the packet journey. DNS finds an address. Your device chooses a route. Routers read the destination prefix, and each hop forwards the packet closer. IPv4. Short dotted decimal, 32 bits, scarce space, and frequent NAT. IPv6, longer hexadecimal, 128 bits, abundant space, and a cleaner path to direct addressing. It is not just numbers. IPv4 is the compact system we inherited. IPv6 is the larger map built for the connected world. Same job, more room to grow. This is cyber clarity.